Hello everyone, thanks for joining another Cyber Skyline Live. I'm Franz Payer with Cyber Skyline and I'm here to help you learn about cybersecurity. We run these episodes for you, so please stick to the end to vote in a poll for our next topic. If you're participating in the National Cyber League, please keep in mind that the team game starts next Friday, the 5th, November the 5th at 1 p.m. Eastern. And you have to sign up your team by November the 4th, going into midnight going into November the 5th. So you have the night before to set up your team. If you don't know how to do that, just go to the NCL registration page. There'll be a link to go and do that. But make sure you have your team set up. If you don't set up a team, you'll still be able to participate in the team game, but you'll just participate by yourself. Highly recommend that you participate with a group of friends. Our surveys show that that's always the way that people get the most enjoyment out of NCL. And plus, having more people on your team means that you'll probably do better. So don't delay and make sure you set up your team. So with that out of the way, this week's topic is DNS, the domain name service or system. I always forget. It'll be on my slides. So without any further ado, I'm going to jump into my slides and please ask any questions that you have along the way and I'll answer them as we go through today's presentation. So what is DNS? It's the domain name system. And it acts as, I could call it an address book. It acts as a lookup to obtain an IP address from a domain name. And so you can see here that we have google.com. Google.com is a domain name. It's any kind of one of those things that you type into an address bar in the browser when you actually use the name of a website. And you might have like mail.google.com, google.com. All of those are domains. The very end, the com part, that is the TLD, the top level domain. You're probably familiar with .com, .edu, .org. Those are kind of like the different extensions for those different domains, right? You can have a different extension. Some are restricted. There's like country specific TLDs like .us for the US, .it for Italy, .ru for Russia. All these different all these different countries, they have their own TLDs, and there's a bunch of new ones that have been being released in the past several years because we've been running out of domain names. And so the solution is to allow more top level domains. So there's more people who can have, I guess Google has to buy more domains. They have to buy google.com, google.ru, google.uk, whatever they are. But you have the opportunity to also buy a domain that might be taken. The .com might be taken, but you might be able to buy the .org version or the .net version. So that's the top level domain and the domain name, and then Google is the primary part, the domain part, and you could have subdomains. So anything before Google, if there's a mail.google.com, that mail is part of the subdomain. The reason why this is very helpful is because you probably don't want to be typing the IP address that you see on the right there, that 172.170.46. However, that is the IP address is what is being used by computers to communicate on the internet. And it's much easier for you to remember that domain name than that IP address. And so for convenience, we've developed DNS to basically provide this lookup behind the scenes so that you as the human, you don't have to remember that Google's IP address is 172.217.0.46. Like that is really annoying to remember. And there's a good chance that it might change in the future. And so the domain name system allows us to just remember google.com or cyberskyline.com or nationalcyberleague.org. Like it doesn't matter what it is, you just remember that name, and it's much easier than remembering that series of numbers. And that's why it exists. And so what you can see here is an example where if you go to your browser, you type in google.com, what actually happens behind the scenes, this is pretty transparent to the user, is that your browser would say, okay, I want to connect to google.com. I don't know what IP address Google has. And so then it asks DNS, who is google.com? And DNS will respond, google.com is this IP address. And then the browser is like, cool, now I will use this IP address to connect to Google services. And so you didn't have to remember that. Your browser would do the lookup for you, figure it out, and get to where it needs to go without any of your intervention. That's why it's so useful. A comparison that I like to make is that if you have a phone and you want to text or call someone, you're probably not typing in their number. You probably entered in their number at one point in time, saved it in your contacts, and then you search them up in your address book, right? You search mom, you search dad in your address book, and you don't search their phone number. I'm sure there might be some people who do that, but generally speaking, you're using their entry in your address book. Well, it's the very same idea with DNS. You can, if you wanted to, type in that IP address directly in your browser, and your browser would know exactly what to do with that. Just like you could type in someone's phone number and call them, even though you've never added them into your address book before. That will work, although for the vast majority of circumstances, you will want the convenience of just typing in google.com and not having to remember all those crazy IP addresses. So it's very, very similar to the concept of an address book within your phone. You want to be able to use the name rather than the actual number, and that's why DNS exists. So how does DNS work? I showed a simplified version in the previous two slides. It's a little bit more complicated than that. And so what we're going to do is we're going to follow this request to go to google.com in a lot more depth. And so the very first thing that you need to be introduced here to is this DNS resolver. That's at the bottom left of the screen here. The purpose of the DNS resolver is to act as, another analogy here would be to act as the librarian. If you wanted to go find a book, and you didn't know how to find it by yourself, you would go ask the librarian, and the librarian would go through all of their catalogs and indices, and they would figure out where the book is. The DNS resolver basically allows for the processing of these DNS requests by multiple different clients. So you might be using a DNS resolver. Typically, all of the devices in a network by default, they're typically configured to use like the DNS resolver on the router, or maybe they're using the DNS resolver on that your internet service provider provides, or maybe using a public DNS resolver. You're typically using a DNS resolver that's being maintained by someone else. And the reason for that is that DNS resolvers will do something called caching. Basically, they will remember the mappings of IP addresses and domain names, so that if you constantly go and you query for google.com, you don't have to keep bugging the actual like domain name servers. You just need to worry about, you just bug your resolver, and your resolver will have it stored in memory, and that will give you much faster response times. And so DNS resolvers are used very commonly and very frequently to be separate entities from your own computer for efficiency purposes. On the right side at the very top, you see the example.com, and I think I messed up here. This is we're going to go to example.com, even though I put google.com in here, but we need to connect to this website, and the IP address there is in parentheses. And so our client, our browser, needs to figure out what is the IP address of that website. And so it needs to go use the DNS service to figure that out. And below that website, you see the DNS root name server, the DNS.com TLD name server, and then the DNS example.com authoritative name server. Basically, the way that the system works for DNS is that it is distributed. There are many, many different servers on the internet that contain information which will help any individual using the DNS system identify what the IP address should be for a domain. But they split up their responsibilities. And so these root name servers, these are the very top of the food chain. Any DNS query will first go to them, and then they will direct you to an authority of the TLD. That's the extension in the domain name. So the .com or the .org or the .net. And they will redirect you to that person, that name server, so that you can ask them for more specific information. They are, the root name servers, they're just there to play that connective tissue and distribute the load of remembering everything. It'd be very impractical for a single for a single server to maintain all of the records for all DNS entries. It's just like the white pages, right? To maintain all of these records for every single website on the internet. It's just not practical. And so all they are responsible for is pointing the request in the direction to the TLD, the top level domain name server, and then those top level domain name servers, they will be responsible for managing all of the records for the .coms. So example.com, google.com, facebook.com, all of the .coms, they are responsible for pointing people at the pointing requests in the direction of those domains and their authoritative name servers. And so the DNS.com TLD name server, that just can tell any request coming in. If I'm trying to go to example.com, it will say, okay, all requests for example.com need to go to that third option, the DNS example.com authoritative name server. And so everyone's just passing the buck until finally you get to example.com's name server, and then example.com's name server will be able to give you all the information about example.com. If there is a subdomain like mail.example.com, it will have that information. Maybe there's a www.example.com. All of those entries are being stored on the example.com authoritative name server. And through this process, you've gone from, I don't know who to ask. I go to the root name server. The root name server will say, okay, you need to go to the people who are responsible for the .coms. You go to the people responsible for the .coms. They say, okay, you need to go to here. And these people are responsible for example.com specifically. And we're going to walk through every single step here. So that first step that I mentioned is that the client makes a request to the DNS resolver. And then the DNS resolver, if it already remembers who is responsible for example.com, then it will immediately take you to example.com. And let's just say in this example, that's not the case. They don't know who's responsible for example.com. And so then they'll ask, okay, do I know who's responsible for .com? And in this circumstance, they don't know who's responsible for .com. And in this case, they must then ask the root name server for example.com, and the root name server will say, okay, if you want to do a lookup on example.com, you need to go ask the .com people, the .com server. And now the DNS resolver finds out which servers are responsible for .com. The DNS resolver will go and ask the .com servers, hey, point me in the direction of example.com. And then the DNS servers for the .com TLD will respond and give the information about the example.com's authoritative name server. And now again, we reach out again. We ask, hey, DNS example.com's DNS authoritative name server, what is the IP address of example.com? And then this green entry here, the example.com authoritative name server, will actually respond with that IP address itself. And then we now know that example.com's IP address is 67.109.85.86. And then that information gets sent back to the client. The client can now go to example.com, and then example.com will give you the HTML for that website. Now, you're probably asking if this .com TLD name server is giving the information about the example.com DNS server, why do we need to ask the example.com name server for the example.com IP address? Aren't these the same thing? And they can be, but typically they are not. The name server here is specifically responsible for responding to these DNS requests. It typically is not also it typically doesn't use its own IP address as the record for the domain itself. Typically, the generic example.com, that's going to point to a website, and the website is going to be run on a different server than the example.com authoritative name server. When you go and buy a domain, let's just say I'm buying example.com, I go through a domain registrar. These are you probably heard of like domain.com or Namecheap. There's a bunch of these different domain registrars, and you go to them and you can say, I want to buy example.com. That'll be $15 a year. You buy it. That means you now own the record for example.com. You can control your DNS entries for example.com. The registrar will oftentimes provide you with a service where they will take your entries for your website, DNS records, and they will host them for you as the authoritative name server. And so let's just say I'm using Namecheap. I bought example.com, and I want to put in my IP address for example.com. I will put that in Namecheap's systems, and then what will happen is that the root name server will point to the .com entry. The .com entry will point to the records that Namecheap is storing on my behalf for my example.com website. So this green entry here is actually not a server that I control. I'm actually using Namecheap servers to respond to these DNS requests because it costs money to maintain your own server, and they provide a little bit of reliability. And so you have this shared service that is being provided by the registrar, by Namecheap.com, and you are not hosting the DNS records yourself. They are hosting it for you. And so when you want to, if someone's trying to access your website, typically that website is being hosted on a different computer, a different server than the one that Namecheap is using to respond to all the DNS queries. So it could potentially be that the authoritative name server for example.com is exactly the same as the computer and the IP address that are hosting your website. Typically, that's not the case, but it is technically possible. You could configure it that way. But what we've seen here with this process is that there's a hierarchy. When you are requesting a lookup for a domain name, it starts at the very top with these DNS root name servers. Those root name servers are basically recorded in the DNS resolver. They're saved there in its memory, so it doesn't have to worry about knowing who they are on the fly. It's information that is hard-coded into the DNS resolver. The DNS resolver will ask the root name servers, can you point me in the direction of the .coms? If I'm trying to go to example.com, they'll get pointed in that direction. And then the .coms will tell you specifically where to find the records for example.com. And then you go to example.com's authoritative name server. And then finally, you can get the IP address of the website itself. So I hope that helped clarify how this process actually works. If there are any questions about that, please ask right now, and I will be sure to address any questions. But in the meantime, I'm going to jump over to how do you actually interact with DNS? Like how can you actually perform a lookup yourself? So when you go and you perform a DNS lookup, you are going to be asking for a DNS record, and there are multiple different types of records. So I have some common ones here. There are a lot more than just these, but these are typically the ones that you will be seeing very frequently. There is an A record, which maps a domain or a subdomain to an IPv4 IP address. There is also the quadruple A record, which maps to a IPv6 address. Why they used 4 A's for the IPv6 and 1 A for the IPv4, I have absolutely no idea, but that's the way that they did it. And so if you want to go to example.com, you are looking specifically for an A record if you're using IPv4 or a AAAA, the quadruple A for an IPv6 address. There's also a CNAME record. This basically allows you to do a redirect. So let's just say I have website1.example.com and website2.example.com. If I wanted to basically send all traffic that was going to, if someone typed in website 1 and I wanted to send them to website 2 instead, I would create a CNAME record. I'd say, hey, any queries coming in to website 1 1.example.com, send that to website 2. And then what will happen is the person requesting the record for website 1 will go through the same process again for website 2. It causes a redirection, and then they'll look at the records for website 2. There's also an MX record. The MX record is used to indicate the email transfer agents for the domain. And so if you have a website that is using email of some sort, they probably have mail records to indicate what servers and transfer agents are being used for all of their email traffic. And there's also TXT records. These are just generic text records which are added to a website typically to verify ownership of a domain. And so if you're using if you're doing some sort of web hosting, sometimes they'll ask you to verify your domain by creating a record in a TXT record in your DNS. And when you're able to do that, they'll give you like a random set of characters, and they'll give you a random string. If you add that TXT record to your DNS records, they'll check to see, is that record actually in the DNS records? And if so, then they know that means you actually do have control to make modifications to the DNS entry, which means that you own that domain for practical purposes. Okay, so let's move on to Dig. And Dig is a program that will actually allow you to make a DNS query manually. So if you go to your browser, you type in google.com, your browser behind the scenes is making that DNS entry. You aren't actually doing that actively by yourself. Your browser is doing that. If you want to do it by yourself, Dig is a tool that runs in Linux, and it's the tool I'm going to show off today in our demo. I'm going to show off a couple different ways that you can use Dig here. So in this very first example, it's very simple. You type in Dig and then the domain that you want to query on. And so in this case, I'm digging google.com. And this will make a request for an A record for google.com. If you specify a record type after the domain, that will allow you to query for a specific type of record on that domain. And so in this circumstance, in the second example, we're doing dig google.com AAAA, and that specifically asks for a quadruple A record for google.com. The default is the A record, so if you want to do an IPv6 address, you need to do the quadruple A. If you wanted to look for a mail record, an MX record, you need just do google.com and then MX. And then this final example here, what we're doing is we are specifically changing the IP address of the DNS resolver that we're using. And so remember that the DNS resolver is your librarian. Your DNS resolver is the server that is actually going and making all of these requests on your behalf. And so by default, when you run dig, there's a setting on your computer that specifies who your default DNS resolver is. If you don't do this at and then the IP address of your DNS resolver, it will use your system default. But by using this at sign, you can actually specify, hey, use this IP address as the resolver, use this server as the resolver instead. The reason why you might want to do this is because you are dependent on that resolver being legitimate and not malicious. So let's just say by default, your computer network is configured to use your internet service provider's DNS resolver, and maybe they're censoring something, or maybe they are being malicious or like redirecting your traffic. They can give you incorrect data. If you try to go to google.com and your DNS resolver is malicious, they can give you a different IP address for google.com than what it actually is. And then now, instead of going to google.com, you're going to a malicious website and you're downloading some malware, right? And so it's very important that your configured DNS resolver is trustworthy. And that's why with Dig, you have the ability to specify that and change that. You can sometimes see different results depending on which DNS resolver you are using. Part of that might be because One might be intentionally doing something malicious. Another reason why you might get different results is that sometimes the results change based on what IP address is closest to you. So for kind of speed and efficiency purposes. But it's actually, the little asterisks there is that it's actually not what is closest to you. It is what is closest to your DNS resolver. And so if you use a DNS resolver on the other side of the world, you might get very, very different results from your queries than if you use a DNS record that is more local to you, because some of those responses that you'll get back will be different depending on the actual, physical distance or the latency between the different devices. So that's how you use Dig. I'm going to go and show you how to do this in Kali Linux. But before I do, I see that there's 2 comments here in the chat. Dave is asking, how does DNS relate to BGP, specifically regarding Facebook's recent issues? So DNS is a very different system than BGP. However, they are both very, very vital for the functioning of the internet. So what DNS does is it provides that directory of how does this domain name map to an IP address. It's only there to provide a directory of telling you who you need to reach in order to get to that website. So we do a lookup for google.com. DNS will tell us what IP address we should go to get to google.com. What BGP does is BGP basically is a system that describes how to get to that destination. This might be a little bit out of scope for today's discussion, but what BGP does in a nutshell is that it basically gives kind of distances connecting between 2 different computers on the internet. And the system basically allows for the game of telephone that occurs when you want to send your data to google.com or facebook.com. Let's just say you have the IP address of facebook.com and you want to send a message to facebook.com. Maybe the message is, I want to go and load the website. When you send your data to your ISP, BGP is what's being used so that your ISP knows where to send your packet next. And then once it gets sent to that next destination, where do they send it to? Where do they send it to? And so on and so forth. So BGP kind of dictates that chain so that people know how to connect to each other at it's not at a device level, it's done at an organizational level. So it's a little bit more complicated, but the TLDR on that is that DNS provides the address lookup and BGP provides the path lookup. Okay, Kevlar's saying here, random thought, IPv4 is 4 bytes, IPv6 is 16 bytes. Okay, so you're saying that potentially potentially it's an A record for IPv4, and the A represents 4 bytes, and the IPv6, there's 4 A's because it's 4 times 4 bytes. It could be, I don't know. Probably can look that up. All right. So if you all have any other questions about DNS, please ask. But moving forward, we're going to go into a demo of how to actually use Dig. So I've got my Kali Linux box here. And we are just going to try to look. This is going to be very simple. We're just going to try to run those commands that I mentioned earlier and get some DNS records. And so from here, I can type in dig google.com. And by default, this will give me the A record for google.com. Okay, so let's break down what is going on over here. When I typed in this command, I got all of these responses. This first line here, this is just kind of like a confirmation. Hey, we're running this version of Dig. We're searching for google.com. We got an answer, and there's some information here. This is DNS specific information. And so there's some flags here. I'm not going to go in detail what these flags are, but we can see that we made one query and we got one answer. And there's one additional bit of information that got sent back. And then below this is the actual results themselves. And so we can see here that under the question section, we asked for google.com, the A record. That's what this A means. And then in the answer section, you can see google.com, A, and then this is the IP address. And so if I copy this and I go into my browser and I go and type this in, you can see that I went to Google, right? I typed in this IP address, and I think what they did is they redirected me so that it would say google.com instead of the IP address. But that, you can confirm that is indeed the IP address of Google. And then if you look at the rest of the items here, query time 15 milliseconds. So that's pretty fast. It took us 15 milliseconds to go and get that response back. And we can see the server. So this is the server. This is the DNS resolver. This is who we went to ask for this lookup. 192.168.88.2. So this is a local IP address. I'm using VMware, so I think this might be piggybacking off of my host's DNS resolution. But you will very frequently see this to be your router's IP address. It might be an IP address of your ISP, or maybe you configured your own resolver and it's your own IP address here. This hashtag 53, the 53 is port 53. So this is port 53 is the port for DNS traffic. So that makes sense. And then we have the timestamp here, and then this is the size of the message in bytes that we received. And so let's actually take a look at this in Wireshark. So I'm going to run Wireshark, and we're going to actually see what does this DNS traffic look like. So I'm going to do a capture. Actually, let me make sure I have these settings correct. Okay. We're starting a capture now for internet traffic. We're going to run our DNS query for google.com. And you can actually see the in between these two queries, we got two different IP addresses. So what might have occurred is, in the meantime, since we last ran this query, maybe this IP address got busy, and so now Google is telling us to go to this other one for some load distribution. But if we do a search here for DNS, we can see here two entries. One is for the request, and one is for the response. And so if I look at this query, I can expand it, and I can see, okay, domain name system query. And here are some options that were set. Here are the queries. And you can see the query here, google.com, type A, class in. I think that's like an inbound request. And then we also requested this opt. I forget what this is for, but there are a lot of like extensions to DNS outside of like the main queries for the standard record types. So this is our request coming in, google.com type A, and the response here, you can see it says we're responding to this query. This is the same query that we provided. And then here's the response, google.com type A. And then here is the IP address for google.com. One interesting thing to note here is that there's a time to live, 5 seconds. So the time to live is how long the resolver should remember this information, how long it should save this information. It's very short. So basically, let's just say that our DNS resolver here was being used by everyone on my local network. Anyone who tries to go to google.com and needs to make a DNS request because their computer doesn't remember where google.com is, they will ask the DNS resolver, and the DNS resolver will only remember that information for 5 seconds. So that means if Bob makes a request for google.com, and then 10 seconds later, Sally makes a request for google.com. The resolver will go through the whole process of doing the DNS resolution again, because it's only supposed to be saving that information for 5 seconds. If this information were like a day, 24 hours, for example, then the DNS resolver would only make that request once per day. And so it looks like Google here is choosing to have a very, very short time to live so that they have a lot of control on updating their records really quickly. But the downside is that they're probably getting way more requests than if they had configured it to be 24 hours, for example. Because if it were 24 hours, then each resolver would only reach out to them once in a 24-hour period. They would get way less traffic. But that's the way that they chose to implement it. Okay, so let's check out a different type of record. Let's check out an MX record, the mail record. And I'm also seeing here we got a question in the chat. Can I use dig for email addresses? So you cannot use dig for an email address. You can only use it on the domain. If you have like example at google.com, you can only do the query on google.com. You can't get any information about the actual inbox itself. But what you can get is information about their mail servers. And so if I do dig google.com here, MX record, and I let me do a new capture here. If I search for this MX record, and we can see here that we have our request, our query here, type MX record for google.com, and then the response. It's acknowledging our query for the MX record. Here's the response. And there's actually multiple records. So on the left side here, you can see that these are all different servers that are responsible for handling the mail for google.com. I can now subsequently do a lookup on these individual servers. So I can do a lookup over here. Let me paste my selection. So you can see here that these 5 different domains, these subdomains, are responsible for handling mail for Google. And then I can then do a DNS query on these subdomains to get the IP address. And so this IP address, 209.85.202.27, this is the IP address of one of the servers that's responsible for handling mail for google.com. And so with our one request for an MX record, we get all of the MX records, right? You can have multiple records. You can actually see here these numbers, the 30, the 50, the 40, the 10, and the 20. These are weights, priority weights, basically allowing Google to say which one you should preference. And so I believe the way that it works is that when you get all of these records back, your computer will try the one with the highest weight, and then if that one doesn't work, then it goes to the one with the second highest weight, and then and it just keeps going down the list until it gets to the end. Hopefully one of them works, and if none of them work, then the connection can't occur, right? The website's not up. I see another question in the chat. Is there a particular downside to having longer TTL values? Yes, there's a very specific trade-off. Basically, the longer your TTL value, the larger the TTL value, the longer you have to wait to propagate and update to your records. So let's just say, for example, that I have 2 different web servers running 2 different versions of my website, version 1 and version 2, and I want to upgrade to version 2, but I don't want to take version 1 down. What you could do is you can put in an update to your DNS record. And so you can say, hey, all the traffic going to my website, instead of going to server version 1, go to server version 2. But if your TTL were like, let's just say a week, then if people already have that information saved, their computers are not going to request a DNS lookup on your website and then get the new IP address of your new server for as long as it's cached, which could be up to a week, right? If someone tries to visit your website a second before you make that change, they are not going to switch to using the new IP address for that new server until that 1 week is over. And that could be kind of a pain if you're trying to roll out some updates to your infrastructure, because it means that you have to leave the other stuff operational in the meantime. Otherwise, if you immediately take down server version 1 and you have server version 2 and your DNS record is correct, people might still not be able to go to your website because they are still trying to use the old IP address that they have a record of, and they haven't switched to using the new one because their cache has not yet expired. And so the reason why I think Google has such a low TTL value is specifically because they want to be able to make rapid changes, without having to worry about things taking forever to migrate. And that's probably why they have such a low TTL value. Now, you might have a different TTL value, like there's a bunch of different TTL values across the board. And so like your computer might decide, hey, I'm going to cache it for longer than whatever that was, 5 minutes or 5 seconds. So there's all these different things to consider about like how TTL and caching is being used to handle the system. The plus side for having a long TTL, though, is that you get less traffic requesting DNS lookups. All right, so let's try doing a request using a different DNS resolver. And in this case, I'm using 1.1.1.1. This is a resolver that is being run by Cloudflare. And so if I run this request, and actually, I'm gonna have to restart my capture here. But you can see in the results that it's telling us that it's using 1.1.1.1 instead of our default over here. And in the packet capture, you can see here, when we made our request the first time around, these previous times without specifying the resolver, this 192.168.88.2, this is what we're seeing in the packet capture. The request is going to 192.168.88.2. If we do a new capture now, and I use 1.1.1.1 as my resolver, and I run this again, you can see that the destination is no longer my default resolver. It is now 1.1.1.1. And we're able to get our results like normal. Another fun fact is that there's also 8.8.8.8, and this is operated by Google themselves. And so you can see here, I got my results from Google's resolver, as well as Namecheap's resolver, or not Namecheap, Cloudflare's resolver. So 8.8.8.8 is used very, very frequently in networking. It's an IP address that people like to ping to see if their computer has connectivity. I do that all the time personally. If I'm trying to figure out like where, if I have issues connecting to a website, I want to figure out like, is it DNS that's not working, or is it that I don't have internet at all? Sometimes if you try to go to google.com and it's not loading, it might not be because you don't have internet connection. It could be because you can't resolve their website records, their DNS records. And so remembering an IP address that you can ping when you don't have DNS working is pretty useful, because it makes sure that it makes sure that it narrows down that possibility for what's happening. If you can ping an IP address like that, that means that you have internet connectivity. If you can't go to a website, it could be a multitude of different problems. The website itself could be down. It could be that the DNS isn't working. It could be your browser having a problem. Like, there's so many reasons why checking to see if a website's working is not a really good indicator of internet connectivity. and using ping on an IP address directly is a much better indication of internet connectivity. And we're all trusting that Google will not fail us and make that go down. We're trusting that that'll always be up. And another reason why you would change your DNS resolver is, like I said before, the concerns about censorship or concerns about malicious attacks from the resolver. Those are all reasons why you might want to use a different DNS resolver. And you can change these settings. You have to change these settings system-wide if you want to make it permanent. So when I did this request here with 8.8.8.8, that's only good for my one request. So any other requests that I make, if I take this out, it'll go back to use my default. So make sure that if you want to change your DNS resolver, you're actually going through your system settings, and it's usually under like internet settings, and you should be able to change this. Oftentimes you get to specify a primary option and a backup option as well. All right. So I think that is everything to cover today. If anyone has any final questions, please ask us in the chat or ask it as a question using the Ask a Question button in Crowdcast. Our next episode is going to be on exploiting VS FTPD with Metasploit. So that'll be a fun one. We're actually going to run an offensive attack using Metasploit. And I'd like to open up, if anyone of you has any ideas for what topics we should cover next, please let me know in the chat. I think next in the queue I have in my mind is covering kind of the basics of coding. So hopefully getting you the ability to be able to read some code and understand it generally, even if you haven't learned how to code. I'm not planning on doing like a full coding class, but hopefully giving you enough ability to be able to Google and patch together some code if you need to write a script or something in the future. Because that's a very important skill to have in cybersecurity. So appreciate you all joining us here today. And let us know again in the chat. Sign up for next week's episode. There's a button for it. And with that, have a great rest of your day. Make sure to sign up for the NCL team game and participate next Friday. And I wish you all the best.